Okay, so the example that I did was cut off and we're having all sorts of technical issues with rendering it. So I'm going to redo, this is the first of two examples I'm redoing, and I'm going to post them as separate videos. This one is asking for the net force acting on this 5 nanocoulomb charge. So we have it sandwiched in between a negative 4 nanocoulomb charge and a 3 nanocoulomb charge. So the first thing I want to do is think in terms of what is the force acting on that charge from each of the other two. I'm going to start with my dot, just my little free body, and I want to look at this. So from the 5 to the 4, it's a negative and a positive charge. So that 5 nanocoulomb is going to be attracted to that 4. So this is F. Let's label these 1, 2, 3. This is F1 on 2. Now let's look at what's going to happen between it and the 3 nanocoulomb charge. When I look at it, they're both positive, so the 5 is going to be repelled from the 3. So I'm going to just draw a little line down there just to make it clear that these are two different forces. So they're being repelled in the same direction. So let's see, this is going to be F3 on 1. Cool. Now, to make my life easier, I'm going to define my axes. I don't know why I just made that a dot for free body. I'm going to define my axes this way, that up and to the left is positive. That way I don't have to deal with negative signs. I like it that way. Now let's do my sum of forces. So my sum of forces in the x, there's nothing in the y, is going to be force 1 on 2 plus force 3, oops, not on 2, on 1. I'm sorry, not on 1, on 2, plus force 3 on 2. And that's going to give me my net force electric charge. Cool. Now remind ourselves that per Coulomb's law, the force Q is going to equal K, my electrostatic constant, times Q1, the magnitude of, times Q2, the magnitude of, divided by the distance squared between them. Now I can just put that in here. I know that both of them are going to have K, so I'm going to factor that out. So I'll have K, let's see how pretty we can make this. Q1, Q2 over R1 squared plus Q3 times Q2 over R2 squared. Okay, so to make this even easier, I can factor out the Q2 too. And I'm going to show you why I'm doing that, because it's going to save you some button pushing. So that's going to be force from the charge. So I'll factor out my Q2. And what am I left with? Q1. Now let's just go ahead and write what those R's are. Now remember, R is the distance between the two charges that are interacting. So for Q1 to Q2, let's see, our Q1 is 4 times 10 to the negative 9. And our R is this 0.500 meters squared. And this is coulombs. And then plus Q3 is our 3 times 10 to the negative 9, that's nano coulombs, divided by the distance between those two is going to be 0.800 squared. And that is going to equal our FQ. So now I'm just going to put that, what's inside the brackets, into my calculator. And this gives me, let's see, my KQ. Let's go ahead and write in our KQ so you can see now why I did that. 8.99 times 10 to the negative 9. And what are our units there? Well, K is going to be such that once I multiply by both of my charges Q, both in which in terms of coulombs, and divide by my meters squared, that I'm left with newtons, because this is just a force, right? So let's see, K has to have units of newtons. I need those charges to go away, the coulombs. So it's going to be times that I have that c squared on the bottom. Now I also need to make the meters squared go away. So meters squared on top. So those are the units of K. K units. So I have my K. We'll go ahead and write the units, why not? Meters squared over c squared times my Q2, which is, I've already forgotten, 5. Oops, not 10 to the negative 9, 10 to the 9. We got 10 to the 9. And then my 5.00 times 10 to the negative 9 coulombs. And then this is times what I came up with in the brackets. What I got 20.69 times 10 to the negative 9. What are those units? Well, coulombs over meters squared. So coulombs over meters squared. Now, why did I do this? With all of the exponents we deal with all the time, it's just easier to look at this. I have 10 to the negative 9 times, 10 to the 9 times 10 to the negative 9. 9 minus 9 is 0. That becomes 10 to the 0, which is just 1. So now I just have essentially 9 times 5 multiplied by what's happening on the inside. And I can double check. I'm going to have coulombs squared, canceling out that. Meter squared on the bottom, canceling out that. And I will finally get what the force Q is. So I'm multiplying my 20.69 times 5 times 8.99. And I get 929.9 nanonewtons, if I will, 10 to the negative 9. Let's do some sig figs here. It just essentially becomes 930 nanonewtons. And there you have it. The next one we'll do it on a triangle.